These next couple slides, I would like to continue to talk about oxygen transport and oxygen transporting finally to the working muscles and mitochondria of the working muscles. So the recent short movie looked at the partial pressure of a gas and the partial pressure of oxygen. Now I want to talk about diffusion of gases. And diffusion is going from a high to low concentration across some kind of barrier. And there are typically a couple different diffusion steps. And the diffusion steps can be from getting out of the lungs and into the bloodstream. Diffusion step would be getting out of the blood and into the tissue or into the muscle cell. And also finally, actually, once it's in the muscle cell, diffusing into the mitochondria where oxygen acts as that final electron acceptor at the end of the electron transport chain. So on the bottom of this slide is a law of diffusion. It's called Fick's law of diffusion. This is out of chapter 10 of our book. And this simply states that the diffusion rate of a gas, so V gas, is equal to area is area, over thickness of that membrane, times some kind of diffusion constant. If it's oxygen or CO2, each of those gases will have a different diffusion constant, and times the difference between the partial pressures, or think of it as the concentrations of those gases. And so let's think about this equation. So if we would increase the area of if we would increase the area of a membrane, what would happen to the rate of diffusion? Well, since it's a direct relationship, as area goes up, the rate of diffusion would go up. If we would increase the thickness of a membrane, and let's think about the lungs, and sometimes in a disease condition or an immune response, the lung tissue can become more thick. So what would happen? So as thickness of that lung membrane goes up, the rate of diffusion is less. If we have a big difference in the partial pressures of a gas, so P1 minus P2, a big difference in those partial pressures will equal a faster rate of diffusion. So this is how, you can think of different gases, but this is a nice relationship that seems sort of logical on how gases will diffuse out of the lungs and eventually into the muscle cell mitochondria. We have a big lung surface area. I think there's a slightly different picture in our textbook now, but it's a big, large surface area of lungs. So as we increase that surface area, the rate of diffusion is greater. And this is, I tried to find a picture online. This just shows that this part of this picture is the respiratory membrane, so the lung alveoli thickness. And the lung alveoli are really, really thin. So the ability to diffuse out of the lungs and into this red blood cell in the bloodstream, since the lung alveoli are thin, then the rate of diffusion is going to be faster. And there's just a couple of numbers to remember off of this picture and picture out of our textbook. One we calculated in the previous short video, and that is at sea level, what is the partial pressure of oxygen at room air? Now that's equal to the percent of oxygen expressed as a fraction, so that's 0.2093, and then times the barometric pressure, which at sea level is about 760 millimeters of mercury. So the partial pressure is in sea level, room air is about 159. So gases want to go from a high to low partial pressure. So what is the pressure in the lung alveolus? We lose some oxygen and some water as well. So it's now at 100. And what's the partial pressure difference then going from the lung into the blood coming into the lungs? Well, the lung at resting conditions, the blood coming into the lungs is about 40 millimeters of mercury, so this difference will be 100 minus 40 or 60. Another good number to remember is that arterial blood is about 100, and it's sort of hard to see in this slide, but it's been estimated that the PO2 way down at the skeletal muscle mitochondria are about 1. So that's 1 millimeter of mercury. And you would expect it to be a pretty low number, as gases want to go from a high to low partial pressure. So we've diffused oxygen out of the bloodstream, out of the lungs and into the bloodstream. How is oxygen then carried in the bloodstream? And almost all, like 90% of oxygen is bound to hemoglobin. And if it is bound to hemoglobin, it's sort of defined, or the terminology is called oxyhemoglobin. If a hemoglobin does not have O2, it's called deoxy. So what is the carrying capacity of hemoglobin in the blood? And a constant that you should remember, and it's the same constant for males, same constant for females. This constant is 1.34. So this 1.34 sort of highlighted too much, but 1.34, that means that each gram of hemoglobin will carry 1.34 mils of oxygen. And here it is for females as well. So that's a good constant to remember. And so now, what's the difference between genders, male versus female? What would be the difference between altitude training? The difference is not a difference in this constant. The difference now is how much hemoglobin we have in the blood. So males, on average, have slightly more hemoglobin, on average 15 grams of hemoglobin in 100 milliliters of blood, and women are slightly less with 13 grams of hemoglobin in 100 milliliters of blood. If we did altitude training, this 15 for males would increase a little bit. And so if we multiply these two together, 15 times 1.34, or if we're up in altitude training, maybe this is now 16 or 17 times 1.34, then this value of 20 for males is the oxygen carrying capacity in arterial blood. So it's about 20 mils of oxygen in 100 mils of blood.